Hi everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher. Everybody, your ma'am is live and I want to know how are you all of you and how is your preparation going on. Now is our organic chemistry quick revision where we are going to revise naming reaction, important reagents that they ask, and I'll give you a simple trick about GOC, not even GOC, I would say electron displacement effect that are usually asked in reactions. Like I will give you a hint about plus M and minus M, right? How you can use them in your reaction. What is meta directing, ortho para directing, and I will also give you a hint about rearrangement of carbocation and tautomerism, because these are some of the things that are directly used in the organic reaction. So let us start this video without wasting any time. Okay, so if your energy is fully high, then I want green hearts in the comment section. Let us start this. As I promise you that I'm going to take maximum of 1 hour, right? Or maybe 1 hour plus 15 to 20 minutes. That's it. So you can start your stopwatch now. Now I'll just start and jump into the lecture. Okay, so starting with the very first thing. Now you will say, ma'am, the speed is very fast. Why? Because this is the revision. Okay, so your focus should be 100% here and not anywhere else, right? Okay, so let us start this. First is going to be Darson's reaction. See the reagents, the initial and the final product. Okay, what is the reactant, what is the reagent, what is the final product? If there is some sort of important thing about that reaction, I'll tell you in between only, right? Okay, just give me a second. I think, okay, now there will be no voice, right? So first is Darson's process. So Darson process is when you have ROH and it is converted to RCl, right? This is in the presence of SOCl2, which is called thionyl chloride. What is the name? The name is thionyl chloride. Thionyl chloride. Thionyl chloride. This occurs in the presence of pyridine. Here this OH is replaced by Cl and this method is preferred. Reason is why this method is preferred so much, because here you have the other byproducts are vapors only. So that is why you get the pure product, that is pure RCl, right? Same reaction, same kind of reaction we have, that is Reed's reaction, okay? Reed's reaction we use SO2Cl2, which is not thionyl. This is sulfuryl. This is sulfuryl chloride, okay? Sulfuryl chloride. Now, if you talk about Reed's reaction, here what you will see, ma'am, in Darson reaction, you had ROH here and rest of the things were same. And here you had SOCl2, right? That is thionyl. In Reed's reaction, you have any hydrocarbon and you will replace the hydrogen with the chlorine. Okay, so by this you add SOCl2, that is sulfuryl chloride. You don't add thionyl chloride. That is the difference between Darson and Reed's reaction, where students usually get confused. Now, next is Sabatier-Sanderson reaction. Usually they ask you this directly. This is basically catalytic hydrogenation in presence of nickel. Here what we do, if we are changing alkene to alkane or alkyne to alkane, right? That is in the presence of hydrogen and the catalyst nickel. If this will occur at around 200 to 300 degrees Celsius. Usually alkene is at 200, less temperature. Alkyne is at high temperature, that is 300 degrees Celsius. Next we have is Wood's reaction, Wood fatigue and fatigue reaction. Okay. So the important point here, ma'am, do I have to remember this whole mechanism? No. Okay. Nobody is asking you to remember the mechanism. Okay. For our quick revision, for the things that we need to solve in the exam, this session is basically not about increasing your knowledge. This session is to gain marks in the exam. Okay, for that we'll study everything on the exam point of view. So if you see this, you don't need to cram this mechanism here. Just remember that what exactly happens here, there is formation of free radical here. Okay, so whenever there is formation of free radical, two alkyl free radicals will join together and that will give you double the amount of hydrocarbon. If here let's say you have 4 carbons and this will have 8 carbons here. So always the number is going to get multiplied by 2. So always you will get even number, or you can say always you will get symmetrical or even number of carbons, as the product unsymmetrical carbons cannot be formed in the hydrocarbon in the product side. Okay. Now what we use here? We use dry ether, because here we are using sodium, which is very explosive. So that is why we have to use dry ether here, right? So sodium, 2 sodium will take out this X and X. You will be left with R free radical. That will be twice, and that will give you RR. That is double the number of carbons. What is Wood's fatigue and what is fatigue? Remember one thing. Woods, you take alkyl halide. Both of them are alkyl halide. In wood fatigue, you take one is alkyl halide, other is aryl halide. But in fatigue, both of them are aryl halide. That is the only difference here, right? Rest of the things are absolutely same. Next, we have soda lime decarboxylation and Kolb's electrolysis. These two reactions are something where students usually get confused, because you are basically extracting carbon dioxide here in both the reactions. Okay. So first is soda lime decarboxylation, where you are going to use quicklime and caustic soda. So together it will be soda lime decarboxylation. But the thing is, when you talk about soda lime decarboxylation, here you have the formation of which intermediate? Carbonyl intermediate. So rate will depend on the stabilization of carbonyl. This is important thing for your JEE questions. Okay, if they ask you difficult questions, they will ask from carbonyl, that okay, this is the intermediate, what is the rate of the reaction? That will be answered by intermediate, that is carbonyl. But if they ask you simple question, that will be, you have RCONA, you have to just know that what is happening here. This COO will be eliminated, right? Na also will be eliminated, and in the end you will have the formation of RH. Why I'm again and again saying you will have formation of RH. That is 1 carbon less. If here you have R plus 1 carbon, here you will have R number of carbon, RH. But if you talk about, ma'am, if we talk about Kolb's electrolysis, in this case, things will change. How the things will change? Here also you are taking out carbon dioxide, but you have the formation of RR. Okay? In soda lime decarboxylation, the same reactant you had, but you had the formation of RH. Okay? But in this case, you had the formation of RR. That means if here you have R plus 1 number of carbon, here you will have 2R number of carbons. That is very, very important. And why this happens? Because this follows the same mechanism as, not same mechanism, I would say the intermediate is same, that is, it follows Wood's free radical mechanism, where R free radical is formed, just like Wood's reaction, where you had the formation of R free radical. That is why in the end RR is formed, right? One more question that they can ask you here, that RR and CO2 are liberated at cathode side, but if you talk about H2 is liberated at cathode side. At anode side you have RR and CO2. At cathode side you have H2. Okay, and the medium, the overall medium, because of this OH negative, is going to be basic. Overall medium in the end is going to be basic. Okay, understood? Till here any confusion, then let me know. Now, usually students know that we can form alkanes from here, but can we form alkenes also? Yes, you can easily form. If you have this kind of condition, this kind of compound, then again what will happen? COO, and this will be eliminated. Here you will have the formation of one bond, so it will give you alkenes. Similarly, if you have already a double bond in the structure, this will be eliminated, this will be eliminated. Instead of this, you will have a bond, and it will give you alkynes as the answer. Got it? Yes, everybody. Now, very good. Next is Reed's reaction. We have already done. Next is Lindlar's catalyst. Now, two reactions that are quite similar to each other. First is, if you react alkyne with Lindlar's catalyst, or if you do Birch reduction, what is going to happen? Okay, so in both the cases you will have the formation of alkenes, but here what you will see, if in the Lindlar's catalyst, if you have used Lindlar's catalyst, which is the hydrogenation only, you are adding hydrogen only, but here that is in the presence of PD, and here to stop the reaction at the alkene. We don't want to have alkene. We want to have alkene. To stop this reaction, we will use a poison, that is PbSO4, or you can use quinoline, or you can use sulfur or CaCO3, whatever it is there. Okay. Now, the important thing is, whenever you have an alkyne, you use Lindlar's catalyst, you will have the formation of cis alkenes, in which two same compounds, two same atoms are sitting next to each other. But if you have the formation of, if let's say you have the formation of alkene only from alkyne, but using Birch reduction, where you use sodium or lithium in liquid ammonia, this is nothing but liquid ammonia, then you will have the formation of trans alkene. Okay, cis alkene in Lindlar's catalyst, trans alkene in Birch reduction. Do you know this Gen Z remember BT? है ना मैम, BT हो गई, BT. Birch reduction gives you trans. Birch reduction will give you trans. Okay. Next is Birch reduction is also has very high level also. This is low level Birch reduction, that is simply asked, right? If they want to complicate the question, how they can do that? So simply what you will do here, let's say this is benzene, right? You add the same thing, reagents are same. So what will happen here? One of the double bond will break, and in the ring you will have only two double bonds, right? So when you have simple benzene, two double bonds will be in front of each other. So this will be the structure that is formed. Either it can be here and here, or it can be here and here. But they should be in the opposite direction with each other. Okay, that means in front of each other, right? But if you have any electron donating group, okay, so how I teach my students that, okay, if someone is giving you something, you would be, okay, you are giving me something, then I'll give a stick around them, right? Okay, because you are getting benefit out of that, right? So if you have electron donating group, then the double bond will be next to it, double bond, and opposite of it, this double bond. So that is why you will get this as the answer. But if you have someone who is always taking away all the things from you, then you will say, let's stay away from this person. Okay, so electron withdrawing group, you will stay away. So in the answer, you will have this double bond in front of this double bond. Okay, but in the answer, always two double bonds should be opposite. That means in front of each other. Is that clear? Okay, yes, everybody. Yes, everybody. Next is Wittig reaction. Okay, Wittig reaction is, you have a ketone, right? And here you have phosphorus halide, right? So here what will happen? This double bond will stay as it is, right? This phosphorus makes 5 bonds. So what will happen here? To this phosphorus, you will attach a double bond O, and this CH2 will come to this side. Okay. In the end, what will happen? Simply, here you already have double bond. Pick this double bond O to this side, right? And this CH2 to this side. That's it. That is going to be your final answer. Okay, that is going to be a final answer. This is called Wittig's reaction. Next is very important, that is hydration of alkenes. So basically in hydration of alkenes, we have 3 processes. One is acidic hydration. In acidic hydration, what happens? You will, in all these cases, you will add H positive and OH negative, but the way you add H positive and OH negative is different. So if you have acidic hydration, directly what you will do? Firstly, you will form carbocation, right? Firstly, you will have carbocation, you will break the double bond, have the formation of carbocation. Then if possible, ring expansion, ring contraction, rearrangement, if that is possible, do that. After that, attach OH negative on C positive, that is that carbocation. Okay. But if you talk about hydroboration oxidation, that is if you use BH3, THF, H2O2, NaOH, all of this together, then that is hydroboration oxidation step. In this case, you don't have to prepare any carbocation, directly use anti-Markovnikov rule. What is anti-Markovnikov rule? Negative, if you negative atom or negative thing will be on the less number of hydrogen. Less number of, wait a minute, anti-Markovnikov, na, this will be more number of hydrogen. More number of hydrogen, right? Markovnikov rule is negative part on the less number of hydrogen. Less number of hydrogen. Markovnikov we use if you have oxymercuration, demercuration, which is this reagent. Okay, you use oxymercuration, demercuration, where directly we use Markovnikov rule, no carbocation, nothing is required here, right? Next is Tidens reaction. In Tidens reaction, what we do? You have alkene, add NOCl, right? Break this bond, Cl will be on this side and NO on this side, and that's it. That is your final answer, right? Bayer's reagent, okay? In Bayer's reagent, that is cold diluted KMNO4. What you have to do here? Basically, this KMNO4 will have pink color, and its pink color will get decolorized. Okay, why it will get decolorized? Because of brown color PPD of MnO2 and glycol. This may or may not they ask you, but definitely this reaction is very important. That is, if you have a double bond, this bond will break, pi bond will break, and you will have the addition of OH on the both side. That is your syn addition. Okay, it will give you syn addition here. Next is Wacker's process. In Wacker's process, what you are going to do? So this is your alkene. Add PdCl2 and CuCl2, right? These are the reagent. Now this CH2 will be converted to this alkene is directly converted to CH3CHO. So if you have to convert alkene directly to aldehyde, this is the process, that is Wacker's process. Okay. Next is Groove's process, or usually we also name it as Lucas reagent. They are quite similar, right? So Lucas reagent is when you have anhydrous ZnCl2 and HCl. This is to distinguish between 1 degree, 2 degree and 3 degree alcohols. Okay. So 1 degree alcohol, ma'am. What is 1 degree? So simply 3 degree alcohol firstly will form, if you talk about the rate of reaction, it's like this. Basically, it forms the turbidity and cloudiness. So what you will see here, that in 3 degree, the turbidity appears immediately. It will appear immediately. Okay, immediately it will appear. If you talk about, ma'am, if you talk about 2 degree, it will appear after 5 minutes. After 5 minutes. But ma'am, if we say, what about 1 degree alcohol? You have to heat it. Even after heating, prolonged heating, maybe after 30 minutes, you will see some turbidity. That is, maybe you will see that after prolonged heating, right? Okay, so that is how you can distinguish 1 degree, 2 degree, 3 degree alcohol from Lucas reagent. Next is Finkelstein and Schwartz reaction. So these are halogen exchange reactions, okay? So in Finkelstein reaction and Schwartz reaction, we change the halogen. So what we exactly do? So you have Rx, you add NaI and dry acetone. So what will happen? This X will be exchanged by I here, and you will have the formation of Ri along with the precipitation in dry acetone. Now why NaX is added here? No, sorry, why dry acetone is added? Because NaX forms the precipitate in dry acetone, and that is the reason we will get a pure product here, right? Okay. Next is you can't use Ri here because this will give no reaction. Next we have Schwartz reaction. In Schwartz reaction, you basically prepare alkyl fluorides, right? That is the RF. For this we use inorganic fluorides. Any of this you can use here, right? Again, this Rx you use, but this X can only be chlorine or bromine. Here also, this X will be either chlorine or bromine, not iodine or not fluorine. Okay. So here you have either chlorine or bromine. You will substitute this. This will be replaced. The X will be replaced by the fluorine. You will have the formation of RF here. This is the example. Okay. Next we have Williamson synthesis. Again, very important reaction. Very frequently this is asked. Williamson synthesis. What are the important points? So you have Rx. You have RONA. Roxarona. Okay, so what will happen? This X and this Na will leave, and you will have the formation of ROR, that is the ether is formed. But ma'am, what's so difficult in this? Why they ask question from here? Right? How they will ask you the question? First is that alkyl halide should be primary here. If alkyl halide is secondary or tertiary, then this reaction will not occur. Here alkyl halide is preferred to be primary. Okay, that is the important thing about this reaction. Okay. Next is Frankland reaction. You remember we did Wood's reaction, right? So similarly we have Frankland and Corey-House synthesis. Okay. So Franklin, we take zinc, right? We take zinc here. Same thing will happen. You will have the formation of RR, but this RR is again not unsymmetrical. But ma'am, in woods also you were getting symmetrical. In woods also you were getting unsymmetrical. In Franklin also we are getting unsymmetrical. We are not getting. Wait a minute. Sorry, my mistake. In woods also we were getting only symmetrical alkenes, right? In Franklin also we are only getting symmetrical alkenes. So ma'am, we want to get unsymmetrical. Our target is to get unsymmetrical. For that we have Fourier house synthesis where you get the formation of unsymmetrical alkenes. Okay, unsymmetrical alkenes you will get here, and this is nothing but this R2CuLi is called Gilman's reagent. Okay, Gilman's reagent. Okay, what you exactly do? Directly you can understand that R2CuLi, we will react this with R-X and you will have the formation of RR-. This is called Gilman's reagent, just like you have Grignard reagent, right? RMgX. This is also organometallic compound, that is Gilman's reagent. Got it? Now, next is diazotization. So, diazotization is when you have aniline, you add NaNO2, HCl, or you directly add or directly you can add HNO2, right? That is also applicable, right? At 0 to 5 degrees Celsius, this will be converted to a disonium chloride, that is N2 positive, Cl negative, which is quite stable between 0 to 5 degrees Celsius. From there, we can prepare a lot of things. Okay, so let us see what are the other things that we can prepare. First is Sand-Meier's reaction. From once we have made disonium chloride, if you react this with the sand, right? Sand means salt. Okay, so we have to react this with the salt of copper. Either salt of copper with chlorine or salt of copper with bromine, right? This will give you chlorobenzene. This will give you bromobenzene, right? If you react this with the CuCN, this will give you, wait a minute, this is Cl, this is Br. This will give you cyanobenzene as well. Okay, understood? Next is Gattermann. Now, Gattermann and Sand-Meier are similar, okay? But here we use copper salt and here we use copper powder. That is the only difference, okay? Otherwise, other things are same only. In Sand-Meier's we use, in Sand-Meier's beta what we use? In Gattermann what we use? Everybody. In Sand-Meier we use salt of copper. In Gattermann, gutter. So for gutter you need powder, right? So here we use copper powder. Okay, so simple. Next is Bal Schiemann. Okay, so Bal Schiemann, she always want to color her bal, hai na? So here what will happen? She wants to do some fashion, right? So here what will happen? You will add fluorine here, right? So that is from disonium chloride only. If you add HBF4, then you will get fluorobenzene. But if you add HBF4, okay, this is Bal Schiemann reaction. But if into this you add HNO2, not HNO2, you add NaNO2, right? Then you add copper couple, then you will get nitrobenzene here. Okay? Then you will get nitrobenzene here, right? Next is Hunsdiecker reaction. So what is Hunsdiecker reaction? Here you have this silver salt of acid, right? Where you add Br2CCl4. This you can remember this by bad criminals. Okay, what bad criminals will do? You are wearing a silver chain, right? And bad criminals will take out this silver chain from you and you will be like, oh my god, I am sweating. So carbon dioxide will be released here and hence you will be left with bad memories. R with bad memories. RBR we have here, just a way to remember things, okay? Right? Next is Dawes process, again a very important process. So basically this CCl bond is very difficult to break because of the partial double bond here. Now what we can do, we need to have very drastic conditions. So that is why we add NaOH at a very drastic condition, that is 623 Kelvin temperature and 300 atmospheric pressure. From there we can get the formation of phenol from chlorobenzene. Because of these drastic condition, it has a specific name, that is Dawes process. Okay. Next is, one more thing. If you add ortho and para position, if you add NO2 or any electron withdrawing group, then the conditions will decrease. Okay, then the conditions will decrease. That is meant that if you add at ortho position, you add NO2, at para also, right? Then you just need to warm it and you will get phenol, right? Because you have electron withdrawing groups on it, right? Next is Ullmann's reaction. This is also a coupling. Basically, this is like fatigue reaction, right? So here, instead of X, you have specific iodine and iodine. When you add copper into it, you will get the formation of diphenyl, okay, just like we did in fatigue reaction, right? Next is cumene process, very important process. What we do here, we have, this is basically called cumene, okay, this is called cumene. So in cumene, what exactly you do? In cumene, you have isopropyl here, right? When you add air, so this will be converted to a peroxide bond OOH, right? So this will be formed OOH. After that, you add hydrolyze it. You will get the formation of this phenol and this acetone here. So you'll have the formation of phenol and acetone. Both the byproducts are very important for you. This they are asking repeatedly from past few years, right? Next is Cole's reaction and Riemer-Tiemer. So in Cole's reaction, both we use phenol as the reactant, right? One we prepare salicylic acid, other we prepare salicylic aldehyde, okay? So talking about Cole's reaction, this is not Cole's electrolysis, this is Cole's reaction. In Cole's reaction, what we do? We add NaOH, then we add carbon dioxide, very important. In this case, you get the formation of salicylic acid, okay? But if you talk about Riemer-Tiemer reaction, you add chloroform and NaOH, and here you get the formation of salicylic aldehyde. But ma'am, if we use here CCl4 and NaOH, you will get the formation of salicylic acid only. Usually this is not asked, but still you should know that if they by chance give you CCl4, then you will get the formation of salicylic acid even in Riemer-Tiemer reaction, not salicylic aldehyde if chloroform is not given. And here the important point is that we have the formation of dichlorocarbene as the electrophile. That is CCl2. This is carbene. Dichlorocarbene will act as the electrophile here. Electrophile here. Okay? This will act as the electrophile. Ma'am, why it is the electrophile? Ma'am, it has lone pair. These are not lone pair of electron. This, if you have understood the intermediates in detail, then you would have known that, okay, carbene is usually electron deficient because carbene has 1, 2, 3, 4, 5, 6 electron. Its octet is not complete. Right? So that is why it is acting as an electrophile. But now we don't have time to do all those things. So just remember, dichlorocarbene is formed. Same thing we will observe in one more reaction, that is carbylamine reaction. Okay, same reagents will be there, same electrophile will be formed. But yes, reactant and products are going to be different in carbylamine reaction. Okay. Next is Kirchhoff's reaction. Now, Kirchhoff reaction only that student will be able to do who knows tautomerism. Okay, that's why I told you in between I have to tell you what is rearrangement, how you do rearrangement of carbocation. That also I'll tell you in the end of the lecture. Right. So here you have Kirchhoff's law, Kirchhoff reaction. So exactly what you do here, this is CH, this is triple bond, this is CH. When you add H2O, what will happen? One pi bond will break here and one point you will have OH, other point you will have H here. Right, this will be formed. Now, this is enol. You have to convert it into ketone. Okay, so what you will do? You will do tautomerism here. So how tautomerism happens? So this is 1, this is 2, this is 3. Just do one thing. This is CH, this is double bond, this is CH, this is OH, this is H. So what you have to do here, from first and second position, this double bond, shift the double bond from 2 and 3 to 1 and 2. That means the double bond now will be there in 1 and 2. Shift this hydrogen from this position to this position. Okay, break the double bond here and shift hydrogen here. Okay, so you will have CH3. This will be the final answer, that is C double bond OH. Got it? What you have to do, I am writing it here beta again. I am writing it here again in the form of in the form of this cloud, that is break, double bond, beta, or you can say break double bond of 2 and 3. Okay, attach double bond of 1 and 3. Okay, break the double bond of 2 and 3, attach the double bond to 1 and 2, sorry, 1 and 2, right? Then what you have to do, shift hydrogen from first to third. Got it? So this is what you have to do. Even if now we have to prepare from ketone to enol, we have to go, even then we'll do the same thing. Let's do it. This is 1, this is 2, let's say this is 3. Okay, 1, 2 and 3. Okay, third will be your alpha carbon. Okay, this is the alpha carbon. So again we are doing the same thing. Break the double bond of 1 and 2, attach it to 2 and 3, shift the hydrogen from 3 to 1. The things will be reversed. Here, that means here you are going to attach 2 and 3. You have to break the double bond of 1 and 2. 3 will be shifted to 1. Okay, 3 will be shifted to 1. Okay, things will be reversed. Got it? Those who are not able to understand tautomerism, I think now it will be clear to you. Right? Is that clear to everybody or not, students? Is that tautomerism clear to you or not? Okay. So that is basically hydration of alkynes, where in the end automatically we have the preparation of aldehydes or ketones. If that is clear to you, then let me know in the comment section. Okay. Next is Rosenman reduction. For Rosenman reduction, you have COCl on adding Lindlar's catalyst, that is directly converted to CHO. This you remember now? What is this? This is nothing but this is Lindlar's catalyst. Okay, Lindlar's catalyst. Right? We did it in conversion of alkynes to cis alkenes. If you remember, conversion of alkynes to cis alkenes, we did this. Right? Okay. Next is Stephen's reaction. Stephen's reaction is you have RCN, you add SnCl2 and HCl. This will be directly converted to RCHO. Right? This will be directly converted to RCHO. Next is Itard's reaction, where you have toluene in the presence of chromyl chloride in CS2. Directly this is converted to benzaldehyde. Okay, Itard's reaction, toluene to benzaldehyde in the presence of chromyl chloride. And Getterman-Koch reaction. Getterman reaction is a different reaction. Getterman-Koch reaction is a different reaction. In Getterman-Koch reaction, benzene we use, not toluene. Here we use CO, HCl, anhydrous ClCl3 or CuCl, and this is directly converted to benzaldehyde. Okay, directly converted to benzaldehyde. How you can remember this? This is Koch na, so this is CHO. Okay, from this you can remember that in Getterman-Koch reaction we convert it into benzaldehyde. Okay, next is two very important reductions, that is Clemenzin and Wolff-Kishner reduction. Reactant and product are same. Difference is in the reagents. Okay. Here the reagent is zinc amalgam HCl. Here the reagent is hydrazine ethylene glycol. Basically, this is in acidic condition. This is in basic condition. Okay. Acidic condition, basic condition. We just reduce the double bond O to H2. This is what we do. Right. Then there is tolerance test. Tolerance test is when you have RCHO that is oxidized to RCO, right? Now in this test, basically ma'am, how in test they can ask you for which thing you use this test, for the identification of which thing. So tolerance test is used for the identification of aldehyde, formic acid. This is very important. Usually students just know ma'am it is aldehyde. No, it is aliphatic and aromatic aldehydes, formic acid, alpha hydroxyketone and hemiacetyl. All these things should be in your mind when you talk about tolerance test. Right? In Felling's test, that is for the identification of only aliphatic aldehyde, not aromatic aldehyde. Okay, don't get confused. Aromatic aldehyde we can't test with Felling test. Okay. So what is Felling test? You have two solutions, Felling A, Felling B. A has CuSO4, B has Rochelle salt, that is alkaline solution of sodium potassium tartrate, that looks something like this. Okay, alkaline solution of sodium potassium, this is tartrate. Okay, basically this is tartric acid, right, and this is sodium potassium tartrate, right. This beta in this intolerance test, you have the formation of AG mirror, that is silver mirror, right? Silver mirror is formed on the tube, but here you have the formation of brown red precipitates. Okay. Next is Benedict test. Benedict test is same as spelling test. The only difference that you will see in Benedict test is Benedict test is used for some demerits in Felling test that were there, right? So Felling test we have to freshly prepare it. Benedict test we don't have to freshly prepare it. We can prepare it before and we can use it after some time also. So here the difference is instead of tartric acid we use citric acid. Rest of the things are same. You have the preparation of CO2 brown red precipitates only from the aldehydes, right? Next, we have haloform, or you can say iodoform test, which is frequently asked. And iodoform test is CHI3, which has yellow precipitates. Okay, which has yellow precipitates. Which can, firstly, what are the reagents that can be used here? NaOH-X2, NaOX, or does not affect, one important point is it does not affect the C double bond C. If you have a double bond, it will have no effect on the double bond, right? Reagents, they can give you this or this, which means the same thing. When you combine these two things, you will get NaOX only, so they can give you any of these things. Now, wait a minute, I think I have not written it here. So, ma'am, aldehyde gives this test or ketones give this test, ma'am? Can you please tell us? Then I'll tell you that. So, if you see, if you have a aldehyde or ketone which has this group, methyl carbonyl group, then it will give the test. Okay. Or if you have a alcohol which has this kind of group, that will give you the positive test for iodoform. Okay. So you need to have either this group or for alcohols you need to have this group, only then iodoform test will be given. That is why this test becomes so important, because they are not saying aldehydes will give, they are not saying alcohols will give, they are not saying ketones will give. They are saying this group or this group is going to give the positive test of iodoform, right? Now we have very important test, that is aldol condensation test, aldol condensation reaction. So here I can't tell you the products directly. So you have to pick the pen and use the notebook now. Okay, so everybody, now you have to use your notebook. So let us start using the notebook. So first is, what is the reagent? Dilute NaOH, dilute KOH, or OH aqueous, or aqueous Na2CO3, or aqueous K2CO3. These are the reagents that will be given to you. Okay, understood? Now, next is, ma'am, if these are the reagents that are given to us, then cross aldol condensation. If you see cross aldol condensation, acha, this so I have not told you the important task now, what you have to, important trick. Chalo, let us see what is the important trick. So if you have to do self-aldol, please listen to this very carefully. This question is very important. You have CH3, CHO. They are saying after self-aldol, what is the product that will be formed? So how firstly you will write the reaction? One molecule you will write, keeping the alpha carbon, something like this, CH2, alpha hydrogen, you should keep it open like this. Other molecule you will write, but now you will keep the carbonyl group open. Here you have kept alpha carbon open, here alpha hydrogen open, here you have kept carbonyl group open, right? Now what you will do, you will simply attach this carbon with this carbon. Okay, you will simply attach this carbon with this carbon. What you will get here, if you are attaching these two carbons, what you will get, this will be, this is going to be CH3. I'll first write CH3, then this is C. This carbonyl carbon is converted to OH. Okay, OH here. and this is H here, this H here. This carbon is joined to this carbonyl, this is C, right? Okay, wait a minute. Array, not this carbon. Oh, mistake. Carbonyl carbon to alpha carbon, na? This is the alpha carbon. Alpha carbon to carbonyl carbon. Okay? Alpha carbon to carbonyl carbon. So how we will write it? This will be, this is CH2. Let us write it on the next page only. I think this page, chalo. First molecule you will write keeping the carbonyl carbon open. Second molecule you will write keeping the alpha carbon open. This is the alpha carbon, right? This is the alpha carbon, right? Now you have to attach carbonyl carbon with the alpha carbon. Okay, that I'll attach here. So keep attaching it. This is CH3. Okay, so this is CH3, this is C. Here this C double bond is converted to COH. Okay, COH, that means double bond O is reduced to OH. This hydrogen is as it is. Okay, I'll keep it as it is. Here, this is bonded to this CH2, right? This alpha hydrogen only that shifted to this O. That is why you had OH here. Okay, that is why I'm not gonna write this H here. This is CH2, this is CH2. After this, remove OH, remove this OH from this position and H from the next position. So what you will have a double bond here. Okay, what you will have a double bond here. Right, this is what you will get in the end. You can keep hydrogen here. Right, this is what you will get as the final answer. Is that clear? Is that clear to everybody or not? Is that clear, students? What is the answer here? Right. Similarly, we will do for cross aldol condensation. Firstly, this will do its self aldol. This will do self aldol. Right. Two products will be there. Right. Then what will happen once they have done the self aldol? Then two more products will be formed. How those two more products will be formed? Let's see that. So here you have CH3, right? This is CH2. This is CH3. This is CH2. Keep the carbonyl carbon open. In the second molecule, if you take, because they are doing cross aldol, right? One self product was made, one self product was already made. Now you are doing the cross product. So if I keep carbonyl carbon of this molecule open, then this alpha hydrogen will be open. CH2, H, this is CH2. Right? After that, what I'm going to do, this carbonyl carbon is attached to alpha carbon. So this is CH3, CH2. This carbonyl is converted to OH. This is H. This is joined to CH2 and this is CHO. Now you take out OH from this side. You take out H from this side. Make a double bond here and hence this is the final answer that you will get. Similarly, if you take, let's say, ma'am, I want to open this carbonyl carbon. So this is CH3, C double bond OH. Plus what you are doing here, this is the alpha carbon. Here, this is the alpha carbon. So you have to open this alpha carbon. So this is CHO. You can just write it as CHO. This is CH. This is the alpha carbon, na? So this is CH. This is H. This is CH3. Okay. Now what you have to do, this is the alpha carbon. You have to join this carbonyl carbon with this alpha carbon. So what you're going to write here, this will be CH3, C. This will be converted to OH. So this is COH. This H is as it is. Then this is joined to this alpha. This is CH. Okay. This hydrogen is already eliminated because it has attached to this oxygen and made OH. So this is CH. To this CH we have two attachments. One is CH3 and the other is CHO. Right? After this, it is going to lose OH and H. But alpha beta unsaturated product is formed. So we know that this is alpha, this is alpha, this is beta. So what you have to do, OH will be eliminated from this side, H will be eliminated from this side, right? And in the end, this is the final answer that you are going to get. Got it? Two self products, two cross products will be there. That is cross aldol condensation. Is that clear to everybody or not? Right? Next is Cannizzaro reaction. In Cannizzaro, it's a disproportionation reaction. So simply what will happen? Same number of carbon, you will have one alcohol, that is CH2OH. With same number of carbon, you will have the formation of one salt of carboxylic acid. Right? So one thing, it is getting reduced. Here it is getting oxidized. So it is disproportionation reaction. In cross Cannizzaro, beta, what is going to happen? In cross Cannizzaro, there is less hindered. Very important. Ma'am, in cross Cannizzaro, you have different products, right? So in cross Cannizzaro, you have to take care of one thing, that here, the one which is less hindered will make the salt. So this is less hindered, so this is going to make the salt, that is HCOONA. And this is going to make, this is more hindered, so that is why it is going to make the alcohol, that is CH3C, that is CH2OH, right? Okay, less hindered is always going to make the salt. I can see in the charts, you guys are doing this and that, this and that, this and that. I can't see anything related to organic chemistry. So do you want me to cancel physical chemistry and inorganic chemistry class? If that is so, I'll definitely cancel it, right? If you don't want me to cancel that, then B, I'm very strict when it comes to these kind of sessions. So no nonsense in the comment section, no nonsense in the chat box. If you're here to study, study. If you're not here to study, you can leave. Okay? Yes, at least don't distract those students who are there, who are here to actually study something. Right? Now, if I see chat box with something, this and that, chit-chatting, girlfriend, boyfriend, this and that, I'll definitely cancel the next class. Right? Okay? Now, next is esterification reaction. So, in esterification reaction, you have acid and you have alcohol. What will happen? This OH and H will leave and you will have the formation of ester here. Right? Next is Helvohal-Zielinski reaction, HVZ reaction. In HVZ reaction, what you have is X2 red phosphorus and water. Here, from the alpha carbon, the hydrogen is replaced by the halogen. That means alpha monosubstituted halo product is formed. On the alpha position, one halogen is substituted. Alpha monosubstituted halo product is formed here. Right? Next is Mendeus reduction. For Mendeus reduction, we have C triple bond N. In this case, these two pi bonds will break and you will have H2 and H2 in both the cases. That is, with the addition of H2Ni and sodium amalgam, you can have the formation of this particular reaction. Okay, this particular product. Gabriel phthalimide reaction, that is only used for the preparation of primary amines, and that too only primary aliphatic amines. Okay, only primary aliphatic amines are prepared here. Okay, not aromatic. So what you use? You have Gabriel phthalimide, you add KOH, right? You add RX, NaOH, water, you will get the formation of this. Ma'am, how? So when you add NH3 here, right, this is basically the formation of phthalimide from phthalic acid, right? You have NH3, you add NH2, NH2 here, you heat it, NH2 will be eliminated, you will have the formation of Gabriel phthalimide. Here, if you add K positive, this will be replaced by K. When you add R positive, this will be replaced by R. Then when you break these two bonds, here you will have H and here you will have H, and hence you will have the formation of RNH2, that is your primary amine. That too we are talking about aliphatic primary amines, not aromatic primary amines. It's a very important point. Very, very important reaction, Hoffman bromamide degradation. And till here, we have done around 51 reactions. And I would say in those 51 also, in one reaction, I have taught you 2-3 reactions, around 55 something reactions we have done, right, in some 50 minutes. Okay. So it's 48 minutes and we have done 55 reactions, I guess, if I include all the reactions. That is a big deal, right? Okay. Hoffman bromamide degradation, you will have amide. This will be vanished and you will have in the end RNH2, right? What we use here? We use Br2 and NaOH here. Br2 and NaOH here. Carbylamine reaction. Let us see in the comment section if you are awake or not. I told you the same reagents we use somewhere else also. And what was the electrophile in that case? If you are able to answer that, that means you are active in this class. Otherwise, so I think you are sleeping only, right? So here it is RNH2 CHCl3 chloroform plus KOH. What will happen? This RNH2 will be converted to RNC. That is nothing but this is called isocyanide, which has a very foul smell. Okay, so this is used to detect primary amine. For the detection of primary amines, we use this reaction. Okay, so this is nothing but this is isocyanide. Okay, isocyanide, which is a false smell, that is used here. Very good. That is very good. I'm so happy to know that. That is CCl2, ma'am, dichlorocarbene is formed. The same thing we did in Riemer-Tiemer reaction, if you remember, right? Okay, very good. Next is Hinsberg test, that is for the distinguished test for 1 degree, 2 degree and 3 degree amines. So in Hinsberg test, what you have to do? See, if you have, let's say, RNH2, right, plus this is SO2Cl, this is C6H5, that is benzene. Again, you have R, this is N, this is H, this is R2NH. Plus here again Cl, SO2, C6H5, this is basically, this is benzene ring only that I am writing simply here. This is R3N. Again, you have Cl, SO2, C6H5. So what it is going to do? This is primary, this is secondary, this is tertiary. Okay, here this HCl is going to get eliminated. You will have the formation of R. This is N. In N, you will have H here, and this is SO2 C6H5. Here, you will have the formation of N. This is R. This is R. This is SO2 and C6H5. Because here again HCl will be eliminated. Here, no reaction will occur because you don't have any hydrogen here to be eliminated. So, for primary means you get a product in which nitrogen has one hydrogen, that is why it is soluble in alkali. Soluble in alkali. Here this nitrogen does not have any hydrogen, so it is insoluble in alkali. Insoluble in alkali, right? And 3 degree will have no reaction because in the starting only, in the amine you don't have any hydrogen. Okay, so that is a distinguished test for Hinsberg reagent. Okay, next is azodite test. For azodite test, what you should remember that basically use disonium chloride here, right? If you have a azodite, that is of phenol. That is of phenol. This is aniline. So what they can ask you is the color. Let us see how many of you remember the color. Okay. Let us see how many of you remember the color. Let us see how many of you remember the color. This is phenol. This is aniline. Okay, aniline. I had given you a hint here. Let us see how many of you are able to answer this. Right here, what will happen? This HCl will be eliminated. You will have the formation of this benzene. This is N2. This is again benzene. This is OH. This is again benzene. Again, this HCl is eliminated. You will have N2. This is again benzene. This is NH2. Right? Let us see. So, hint was because phenol, you have O here. So, that is why orange color, I have also given you the color here. Orange color of dye is formed. Right? In aniline, you have yellow color of dye. You have yellow color of the dye. Very good orange color, ma'am. Very good, very good, very good, very good, very good. Acha, what about this one? If you have beta nephthol, this is nothing but this is beta nephthol. Okay. For this, what you have, because this also they have asked you in JEE, okay. So this, if you eliminate, you will have the formation of this is benzene, this is N2. Here you have this benzene, this is OH, this is again one. Okay. So now this is having which color? This is having, let me see, beta. What is this color? This is scarlet red color. Scarlet red color. Okay. Red color. Okay. Or you can just remember red color dye is formed here. Right. Next is Hoffman ammonolysis. You have amine here, you add Rx, right? That is converted to 1 degree amine, right? You again add Rx, that is converted to 2 degree amine, right? You again add Rx, that is converted to 3 degree amine, okay? That is converted to 3 degree amine. Ma'am, we want to add Rx, then that is quaternary salt is formed. Quaternary salt is formed here. Okay. Quaternary salt is formed here. Got it or not? Right? Okay. Next is pinacolone rearrangement. So what we are going to do here, pinacolone rearrangement. This is pinacol, which has two OH and OH here. Okay? When on the adjacent position you have two OH, what you have to do, how it is going to rearrange? You add H positive acidic conditions. OH, this will gain the H positive and it will be converted to O positive H2. That is this thing. Okay? O positive H2, this will be eliminated. You will have the formation of this carbocation. Then this R will get shifted to this side because okay, R will get shifted to this side. Now what you will have the formation of a carbocation in which directly on that carbocation you have the attachment of OH. Now back bonding, because of back bonding, if you know the concepts of GOC, because of back bonding here, this is a very stable thing, right? Okay, so now what will happen because of this back bonding? Now what will happen? This is Cr3. Now the electrons will be donated here, H will leave from this side, and hence you will have the formation of this pinacolone. That is a ketonic group is formed here. That is pinacolone rearrangement. Beta, very rare chances are they will ask you this in JEE mains. If they actually want to ask something difficult, they will ask you pinacolone rearrangement for sure. Because most of the students, they skip these kind of reactions, okay? Cumene process, beta, we have already done, right? This also we have, this we have not done already, but yes. Next beta, we have Shortman-Bowman reaction or benzoylation reaction. What you do here, you have aniline, right? This H and this Cl will be eliminated. You attach these two things here. That is, this is benzene, NH. NH will be attached to this carbon, CO and benzene. So that is called benzoylation. When you are adding benzene, CO, benzene into this. Okay. Stephen's reduction, as I told you, if you add SnCl2 in Cn, you convert this Cn to CHO. That is called Stephen reduction. We have done this today class only. We have done this before also. But if they prepare SnHCl or FeHCl, then that is not Stephen. Stephen is when you add SnCl to an HCl. Okay. SnHCl and FeHCl is not Stephen's reduction. Then there is Victor-Mayer test, right? For 1 degree, 2 degree, 3 degree alcohol. Ma'am, do I have to learn everything here? Victor-Mayer test, you don't have to learn it thoroughly, right? Just remember, for primary, when you use all these reagents, you get red color. For secondary, you get blue color solution. For tertiary, you get colorless solution. Because Victor-Mayer test is not frequently asked to you, right? But still I have put it here. Even if they ask you, they can only ask you for primary, what is the color, for secondary, what is the color, for tertiary, what is the color. You don't need to get into detail of this thing, okay? Then ma'am, why you have put Lissagany's test here, ma'am? That is not in the naming reaction. Because usually the students who are thinking of skipping practical chemistry, they will skip this also. So that's why I have put this test here. In JEE attempt 1, they have asked 3-4 questions based on this, right? So here it is, Lissagany's test, you have sodium extract, sodium fusion extract you prepare, that is Lissagany's extract, right? So if let's say you have CNN, you have the preparation of NaCN, right? With NaCN, you will get the preparation of this Prussian blue color, right? This Prussian blue color, that is ferrous ferrocyanate, that will be formed here, right? Okay, if you have sulfur, in that case you will have Na2S, where on this reaction you will have the preparation of purple color, okay, purple, or you can say violet color compound is prepared, that is Na4 FeCN5NOS. This is also a very important compound. This is also a very important compound, right? Next we have some important reagents, okay. Okay, students, shall we start with the important reagents now? Shall we start with the important reagents? I told you I'm going to take 1 hour and 15 to 20 minutes extra. So in 20 minutes, I'm going to finish this lecture. Let us see the chlorinating reagents. Okay, chlorinating reagents means which will replace OH, OH, OH with the Cl. Okay, so all the OH, we are going to replace it with the Cl. Or OR here is also replaced with the Cl, that is the chlorinating agents, right? Next is KNO. So if we talk about KNO, we know that KNO, or you can say KCN, both have ionic nature. Okay, both are basically, we have in KCN or KNO2, this is ionic compound. That is why what will happen here, O negative is free and here C is free. Here C negative is free. That is why when you prepare the halide here with, when you react alkyl halide with KNO2 or KCN, you will have the preparation of RONO or RCN, right? These are some of the very important reactions. But if you prepare this with AgNO2 or AgCN, here you will have the preparation of RNO2 and here you will have the preparation of RNC. Here this was reacting with oxygen and carbon. Here because with Ag, it is preparing a covalent compound. It is basically a covalent bond. That is why here oxygen is not free for the bond. Here carbon is not free for the bond. That is why you have RNC and RNO2 as the product. Next is alcoholic KOH. So talking about aqueous AOH. Aqueous KOH beta, it is only going to replace, OH, or you can say X with OH. Okay, this is going to only replace the halogen with the OH, nothing else. But if you talk about alcoholic KOH, it is going to replace, it is going to cause elimination, that is dehalohydrogenation. That means if you have a, let's say you have any compound, let's say 1, 2, 3, you have halogen here, you have hydrogen here. So halogen and hydrogen will be eliminated. You will have the formation of alkene. You will have the formation of alkene, which will be ZZ product. ZZ product means high alkyl substituted. High alkyl substituted product will be formed here. High alkyl substituted product will be formed here. Next is, if you have alkane, that usually does not react with KMNO4, LiAlH4, NUH or H2SO4. But if you have a tertiary alkyl like this, okay, with this carbon has 3 CH3 groups, in that case, if you add KMNO4, then this hydrogen is replaced by OH. Again, this is also a very important reaction. Next is dilute KMNO4. This beta we have already done. This is nothing but this is the Bayer's reagent, right? Next we have mild oxidizing agent. Okay, wait a minute. Yes, mild oxidizing agents like PCC, PDC, CrO3, right? These are mild oxidizing agents. Strong oxidizing agents are cold MnO4, Jones reagents, like when you use CrO3 in presence of H2SO4, then that will be a strong oxidizing agent. So if you have 1 degree, 2 degree alcohol, so simple thing is, if you have 1 degree alcohol, then in if you have mild oxidizing agent, wait a minute, here I'll just write, okay, I'll just write it here. If you have mild oxidizing agent, if you have strong oxidizing agents, right? So how you are going to distinguish that? So simple is, if you have 1 degree alcohol, for mild oxidizing agent, you will have the formation of aldehydes. And with strong oxidizing agents, you will have the formation of carboxylic acid. For 2-degree alcohol, for mild oxidizing agents, you will have ketone. For strong also, you will have ketone. But with 3-degree, no reaction is here, and here also you will have no reaction. That means 3-degree alcohol give no reaction whether you use mild or strong oxidizing agents. Nothing will happen here, right? But with this, I'll tell you also one more very important thing. That is, if you have copper and 300 degrees Celsius or 573 Kelvin, then with 1-degree alcohol will give you aldehyde. 1-degree alcohol will give you aldehyde. 2-degree will give you ketone only. But the important thing is 3-degree will start giving you alkene here. That is the important part. Okay? If you have MnO2, then in this case only the allylic alcohol is oxidized to CHO. That means allylic means this kind of thing. You have C, this alcohol. If to that OH, to that carbon where OH is attached, that is attached to a double bond, that is the allylic position, then only this will be oxidized to CHO. Okay, only allylic position when you have MnO2. Is that clear to everybody or not? Is that clear to everybody or not? Now, let us see, wait a minute. Okay. Now let us see hot concentrated KMnO, the story of KMnO4, right? A very important reagent, that is KMnO4. How does it behave with different things? Okay. So when you talk about hot concentrated KMnO4, what it is going to do, beta? Very simple thing I'll tell you here. Whatever you have, 1-degree alcohol is directly converted to carboxylic acid. Basically, what is happening? So this is your 1-degree alcohol. Let's say anything that is directly converted to carboxylic acid. Okay. But if you have 2-degree alcohol, so this is a 2-degree alcohol, OH is attached to 2 carbons. OH is attached to that carbon which is further attached to 2 carbons. That is also converted to carboxylic acid only. This is the full step, okay? So what you have to do directly, okay? What you have to do directly. So basically, we know that when you have 2-degree alcohol, that is converted to ketone, okay? But now, because you have hot concentrated KMnO4, further oxidation will occur, right? So what will happen here? We have double bond O. This will be tautomerized here. This is 1, 2, 3, right? This double bond will turn into, this double bond from this position will get converted to this position, right? And this hydrogen here will be shifted to this position. So you will have tautomerization here. You will have tautomerization. Okay? Once you do the tautomerization, you have a double bond. Now, this double bond will break. Okay, how you will break this? This double bond will break. You will have the formation of double bond O here, double bond O here, right? And rest of the hydrogen, if to any carbon you have the attachment of hydrogen, that will be converted to. So basically, what we are doing, break the double bond, attach double bond O here, double bond O here. Just like we will do in ozonolysis. Break the double bond, attach double bond O, attach double bond O. So this is RCOH double bond O plus this will be CHH double bond O. So when you are using hot concentrated KMnO4, the carbon that is attached, the hydrogen that is attached next to the carbonyl carbon is also converted to OH. This is nothing but H2CO3, which will get converted to water plus carbon dioxide. Is that clear to everybody or not? Same thing we will do in case of ozonolysis as well. Okay, break the double bond, attach double bond O, double bond. Okay, firstly let me teach you ozonolysis. Okay, so if you see ozonolysis now, okay, firstly see ozonolysis. Ozonolysis is of two kinds, reductive and oxidative. Reductive ozonolysis, you use Zn, O3 you are using in both cases. Here you use Zn or H2O or Me2S. Here you use H2O2 or hot concentrated KMnO4. Okay? So in reductive, what you do, in reductive you have C double bond O. You break the double bond, attach double bond O, attach double bond O. Okay? In oxidative, you move one step further. The carbonyl carbon, the hydrogen attached to carbonyl carbon, directly is converted to OH. Beta, is this thing clear to everybody or not? This is going to solve so many questions, okay, in your exam. In reductive, you have break the double bond, attach double bond or double bond O. In oxidative, move one step further, convert all the hydrogens to OH that are directly attached here. Okay, understood? Understood or not? Same thing we have done here. Break the double bond, attach double bond or double bond. Then you got the formation of, here you got the acid only, that is this. Here you got the formation of CH double bond O. Now all the hydrogens that are attached directly to carbonyl is converted to OH. Now we know that this is nothing but H2CO3, which is not at all stable. This is directly converted to H2O plus CO2. So directly we have written CO2 here. Is that clear to everybody or not? Right? Okay, chalo. Next is same with 3-degree alcohol. So they will not ask you this, but still, okay. This I have just shown you that how you are going to do things. 3-degree alcohol will not get oxidized unless and until you give hot concentrated KMnO4, right? So this is directly converted to this OH will be eliminated. This is CH3. Here one hydrogen will be eliminated, okay? And hence this double bond will jump here, and this is the formation that you will have, okay? This is the alkene formation you have. Once you have the alkene formation, break the double bond, attach double bond O here, attach double bond O here, right? So you have this formation, and here what you have, see, if you see this here, this is CH3, this is CH3, this is C, this is CH2, okay? You break the double bond here, attach double bond O here, attach double bond O here, okay? What you will get here? What you will get? You will get the formation of an acetone from this position. From here you will get again, this is HCH double bond O. Okay? From CH2 you will get this position. This will be converted to, this is OH, this is OH. This will be reduced to CO2 and H2. Got it? The same thing we did here. We are applying the same concept of ozonolysis here. Same concept of oxidative ozonolysis. Got it or not? Is that thing clear to everybody or not? Right? Okay. Ozonolysis also done, this done, this done. Next is dehydrating agents. So dehydrating agents that take out water, concentrated H2SO4, concentrated H3PO4, PCl5, P2O5, concentrated H3PO4 and POCl3, all are good dehydrating agents. So they are going to eliminate water. Okay, wherever they will eliminate water from alpha and beta positions. From the adjacent positions, they will eliminate water. Okay, next we have is concentrated H2SO4. Now we are saying it is a good dehydrating agent, but if you are using it at 170 degree, it will give you alkene. But if you are using it at less temperature, that is 140, so what will happen? It will eliminate water from two different alcohols. Okay, so you have OH here, you have CH2, CH3. It will eliminate water from two different, and it will then give you ether. So it also depends on the temperature in case of alcohols, right? Then talking about terminal alkynes. For terminal alkynes, this is very acidic in nature. This hydrogen is very acidic in nature. So when you use ammonical solution here, this is directly converted to white precipitates. And when you use Cu2, Cl2, NH4OH, this is converted to red precipitates. Okay. Next is hydrolysis. So hydrolysis also is asked to you in between some reactions. So when you have amine, that is double bond NH, that is directly converted to acetone. When you have CN, right, if you do hydrolysis again and again, with one hydrolysis, it is converted to amide. With one more hydrolysis, this NH2 group is converted to OH, that is acid. If you have NC, again those pi bonds will break here and it is directly converted to RNH2 and HCOH, right? Next is allylic bromination, very important. Okay? Allylic position I already told you. So if you have NBS, that is N-bromosuccinimide, or you have Br2 in the presence of sunlight or at a very high temperature, that means you are going to replace the allylic, this is the allylic position, this is the allylic position, right? So you are going to replace the allylic hydrogen with bromine, okay? That is going to be the substitution that you are going to do. If you have sunlight, high heat or N-bromosuccinimide, only then this will occur. Next is one very important reagent, very important reagent, that is ether plus concentrated HI. Okay? Just like Williams-Son synthesis is very important, this is also very important. Okay, these are all not naming reactions, these are important reagents. Okay, so ether plus concentrated HI. You have ROR, right? You add concentrated HI here. What will happen? You will get the formation of, break this bond, this is RI and ROH. But the thing is, ma'am, should I break this bond or should I break this bond? That is the main question. Okay, so for that, what you will do, if you have R and R dash are primary, this one and this one both are primary, then it is going to follow SN2 mechanism. That means I will be attached to that place where less steric hindrance is there. That alkyl group which is less sterically hindered, that will be your iodide, right? Only if this is, both are primary. If one of them is tertiary, then it will follow SN1. So basically SN2 is that mechanism in which you have transition state. Okay? That is why we are talking about hindrance here. Okay? That is why we are saying I will be attached to less hindered alkyl group. If you have SN1 reaction, that means carbocation formation. So in this 3 degrees more stable, that is why where carbocation is more stable, that means we will choose that alkyl halide which is carbocation is more stable. Okay, understood or not? Very important. Next is the difference of some reducing agents. We just did oxidizing agents, so now we are going to do reducing agents. Reducing agents like LiAlH4. Okay, so LiAlH4 very important. It can reduce carboxylic acid, ester, acid chloride to alcohols. It can reduce amides, amines or NO2 to corresponding amines. Okay, amides or NO2 to corresponding amines it can reduce. But talking about, if you talk about, this, so we have done now. Okay, chalo. Next, okay, I forgot that there was one more point here. Yes, it is not going to reduce double bond. It is not going to reduce something like this double bond, that is CHO. Now, if you have double bond and CHO, that means if double bond is simple, then it is not going to reduce that. But if to a double bond, you have some electron withdrawing groups attached here, then it is going to reduce that. Okay, then everything will be reduced here, right? Next is talking about NaBH4, very important. Do not react with RCH, acid, amide or ester. This is a very important point. Because they ask you questions from here that you are given with a reactant. LiLH4, what is the answer? NaBH4, what is the answer? LiLH4 will react with this and this, all of them. But NaBH4 will not react with acid, amide or ester. Very important, right? So, it can only reduce aldehyde, ketone, acyl chloride, right, amine to alcohol, right? Or these are the reactions that is given to us, right? How it can reduce. This is to alcohol, this is to alcohol, this is also to alcohol, this also to alcohol. Okay? Next is Dibble, diisobutyl aluminium hydride. Dibble, acyl is converted to aldehyde, you have ester is converted to aldehyde, you have CN is converted to aldehyde, you have acid that is also converted to aldehyde in case of Dibble, right? Then if you have B2H6 and THF, we are not doing oxidation here, right? So directly double bond, this will break, you will do the reduction here. Directly this is also directly converted to alcohol. This amide is directly, this bond will break, here you will add H2 directly converted to amine here, right? But with COCl, C double bond NOH and RH, it has no reaction, nothing, no reaction is given here, right? Then there is Grignard reagent. So Grignard reagent basically shows two kind of reactions. I'll just simply tell you. One is with the proton source. This is Grignard reagent, that is RMGX. Okay, two kind of reactions it shows. This is RMGX. If you have given any proton source, water or alkyne is also very good proton source, right? So what will happen? It will directly get converted to RH, right? That means hydrocarbon is directly formed. Okay. But if you have any carbonyl compound here, okay, any carbonyl group, and you have RMGX, then what will happen? Then it is, we know that this is partially positive, this is partially negative, this is partially positive, this is partially negative. Now it is going to attack on the carbon, this is going to attack here, right? So basically it is going to get attached there, and you will get C, this is OMGX, right? This is 1, 2, and here you will have the formation of this R. And after the hydrolysis, this is converted to COH. This is 1, 2, and this is R. That is the difference if you have a proton source or if you have a carbonyl carbon, or even if you have C triple bond N, it does the same thing. Okay. So these two reactions of Grignard reagents are very important. Grignard reagent is also frequently asked. Right, I think we are left with how many? We are left with 1, 2, 3, 4, some 5, 6 pages we are left with. Let's do that. Right. This is hemiacetal, acetal, ketal, and hemiketal. Okay. So when you have aldehyde, you give H positive here. Right. This H positive will be there with this oxygen. Right. This will take away this electrons from here because oxygen can't have positive charge. Then you will have the formation of this hemiacetal here because one more ROH group will attach here. So hemiacetal is when on the carbon one is OH, one group is OR. But acetal is when on the carbon both the groups are OR, that is called acetal. Okay. If you further give it one more ROH, then this OH is converted to OR, that is acetal. Okay. Talking about this, if you have ketone, this is from aldehyde, you get acetal and hemiacetal. But if you have ketone, if you do the same thing, because this is tonic group 1, H positive will be attached here because you give it H positive, electrons will jump here, right? Then again one O group will attach here. Now hemiketal is when to this carbon you have two R groups, one OH and one OR. Hemiacetal is you have one hydrogen, one R group, one OH and one OR. Okay, that is the difference. Hemiacetal and hemiketal, this is the difference. This is the difference. This is RR, this is RH. Hemiacetal and acetal, this is the difference. This is OH, this is OR. Similarly, here if you add one more ROH, this OH is converted to OR. Okay? Ketal is also formed in one more way, that is if you use ethylene glycol, this oxygen and this two water, this two hydrogen will be eliminated as water, and you will have the formation of this cyclic chain. That is why this ethylene glycol, this ketal is formed to protect the ketonic group. Okay, we always say that ketal is formed, we form ketal to protect the ketonic group because here we are protecting the ketonic group. Okay, that is also one very important point, right? Next we have cyanohydrin beta, this I already told you, right? So if you talk about, let's say this is ketone and this is KCN, right? So what will happen? This is positive, this is negative. This negative will attack here, electrons will jump here, and hence you will have the formation of CO negative, CN, this is R, this is R dash, this is converted to H positive, so it will be cyanohydrin is formed here. Right? Now, these reactions are very, very important. Basically, these are the reaction of semi-carbazone, shift base, oxime. On the JEE mains channel, I think within 1 hour, I'll send you one page, okay, of your NCRT. I'll send you one page of your NCRT. Okay? That page you have to do where what is this Z? Where in the NCRT they will give you different values for the Z, and according to your product will change. Okay. So let me just tell you what exactly is this. So here what you have, O and NH2 You have this here. What will happen? This O and this H2 will be eliminated. Then carbon with double bond and nitrogen. Carbon double bond and nitrogen, that is carbon double bond nitrogen, and this Z will be attached here, right? So according to this, you can form 2,4-DNP, Schiff's base, oxime, imine, then semicarbazone, all these things you can form. That table I'll send you, okay? One table I'll send you, right? Wait for that table, because you never know, directly the question will be asked from that table, okay? Those students who are actually not sleeping in the class, they will be very benefited from that. Now, next is, if you had some electrophiles here, like here you have the electrophile generation, that is X positive. With concentrated HNO3 and H2SO4, you have NO2 positive. With RCl anhydrous AlCl3, you have R positive generation. With RCOCl and anhydrous AlCl3, or if you have acidic anhydride, then you will have the formation of RCO positive electrophile. If you have concentrated H2SO4 or oleum, you will have the formation of SO3H electrophile that will attack, right? Okay. Now, beta, one thing that I told you that I'll tell you from GUC, okay, which is important to understand in organic chemistry reactions, that if you have on the benzene ring, if you have a group that has lone pair of electrons, okay, if you have a group that has lone pair of electrons, it is always going to, just make it like this. If you have a benzene ring, right, okay, and you have a group attached that has lone pair of electron, it is always going to donate the electrons. That means it is always going to show plus M effect. It is always going to show plus M effect. And because it orthopara, see, plus M effect is always going to be orthopara directing. Okay? But if you see, you have a benzene ring where you have the attachment of a group which is double bondedly or triple bondedly attached to some more electronegative group, then it will always take away the electron. It is always going to show minus M effect, and minus M group are always meta directing. It is always going to be meta directing. Usually these groups are, beta, remember, these groups are activating. Usually these groups are activating, and these are deactivating groups. But the exception is halogen. Okay, halogen is showing plus M and minus I effect. Okay, here you have GUC, but minus I is more dominating. That is why it is deactivating but orthopara directing. Okay, so always if you have any halogen, the rate of reaction will be slow because it is a deactivating group, but it will always be orthopara directing. This is an important thing that you should note down. This is very important for your organic reactions. Okay, rest is final 2-3 pages related to your amines, from where they can directly ask you the question. First is that when you talk about OH, alcohol, okay, one is when you add Br2CS2, then directly you will get orthopara product. But when you add Br2 in water, you will get tri-substituted product. But in aniline, what happens? You always get tri-substituted product. So to get only para-substituted product here, what we will do? We will do the acetylation. That means we will add CH3CO here. So when you add CH3CO here, these lone pairs are involved in this resonance. That is why you don't have the that is why when these lone pairs are involved in the resonance with CO, they are not very activating. That is why they only form para-substituted product, and after the hydrolysis, right, you will have the formation of only para-substituted product. So they ask usually that why you do acetylation to form para-substituted product. One more thing is that whenever you do nitration of anilines, you get, we know that aniline you have lone pairs here, so it should be orthopara directing. But very exceptionally, you get here, very weird thing is you get meta product also. That to 47%. So, ma'am, why we are getting meta product, ma'am? Why we are getting? Because the reason is you have the formation of, see, reason is because of concentrated HNO, concentrated HNO3 and H2SO4. This is an acid. This is acidic condition. This is a base. So this base is going to abstract proton from the acid and it is going to get converted to anilinium ion. Okay. And this anilinium ion is meta directing and that is why you have 47% meta product here. Now we have to make this lone pair busy somewhere so that we don't get anilinium ion here. That is why we again do acetylation. Now this lone pair is busy in the resonance. That is why here you will get only the para substituted nitro product. Okay, again a very important point. Last is if you want to convert disonium chloride directly to benzene, this reaction is also very frequently asked. Directly to benzene, use H3PO2 or ethyl alcohol or HCOH, right? Then directly you can convert disonium chloride to benzene. Okay, is that clear to everybody or not? Beta, we have completed how much time? 91. Chalo, 10 minutes extra I took, right? But so many things I taught you in between, right? So I don't think so. You should, if you the students who are watching this at recorded and they are thinking that I'll study this at 2x speed, beta, I am already speaking in 2x speed, right? So I don't think so. Your brain will be able to absorb all the knowledge that I have given you in this lecture at 2x speed. So kindly don't watch it at 2x speed, watch it at 1x only. Yes, if you are doing fast revision, you know all the concepts already, then you can watch it on 2x speed. But if you're listening this for the first time, maybe some things you won't be able to understand for the first time. You have to revisit that point and you have to rewatch that particular reaction. If you're watching, if you're learning some reaction for the first time, if you're learning this reaction for third and fourth time, you're doing the revision, watch it at 2x speed or 1x speed according to your retaining power. Okay? Yes, everybody. So we have completed today's task. Now on Saturday and Sunday, we are going to quickly revise physical chemistry formulas and also inorganic chemistry exceptions, right? Okay. This was the major chunk of this because I have not only taken naming reaction, not only distinguished test, but also the important reagent in this particular lecture, right? So now all the students who are looking to prepare for JEE Mains 2 and VIT-EEE, KCET, Comet K. So for you guys, we have a batch where basically in this crash batch, we are providing you not only JEE Mains 2, but also VIT-EEE. If you purchase crash combo, you will also get KCET and Comet K test. And if you go for Crash Pro, you will also get printed JEE previous year question delivered at your home, right? So all these things are provided at these 999, 1999, 2999. According to what you need, you can purchase any of this. And if you're looking for any of the test series, first of all, like this session. All those who have not liked it, let me see how many likes you have given to this much hard work that Diksha ma'am is just too very bad. Just 144 likes. Very bad. Very bad. Very bad. And then you say, ma'am, we love you. What is this kind of love? What is this love? Huh? Not even likes, no comments, right? So much hard work I do for you. All the handwritten notes I have provided you, right? No slips, nothing I have taken, right? So this so deserves a lot of love. Like Nalini is giving so many green hearts, love, red hearts, everything I think I deserve, right? Okay. Now, if you see this in the description box, you will see a lot of things. That is last minute test series, main attempt to English batch. Okay, last year last mile test series. That is JEE main test series. That is already there. Right, go and purchase that. That is for this time only what you need. Right, in these days, what you are left with 5-10 days, you have to purchase this test series and start preparing, start giving the mock test right by yourself so that you can very well prepare for the exam because the time management is very tough task. That will be you will be You will get pro in that. Next is Extra Mile Engineering Test Series 2025, right? So here what you will get, each test series contains 10 full syllabus tests, 10 engineering exam test series it is, right? Exam includes MHT-CET, KCET, VAT-EEE, XAM-CET, ISR, SRM, JEEE, KIT-EE, WB, West Bengal, okay, BITSAT, then COMET-K. So many tests we have included, and here that is that you can purchase over here, right? Okay, view course plans and you can get it, right? Okay, at 999. Next is JEE 2025 crash batch that I have already told you about, right? And JEE and MHT-CET online courses, right? That is also, you can enroll yourself into that. MHT crash course, beta, it is available here. And if you're preparing for JEE Advanced after JEE Mains, then this batch is for you. That is Eklavya batch. Okay, okay, that is Eklavya batch where students are already getting prepared for their JEE Advanced. Okay, so all these are the all things that you will get in the description box. Everything will be provided to you. You can yourself see if this is the content that we are providing you for free of cost and what we will provide you if we charge you something. Okay, but the charge is very less, the fees is very less. Now, all the students here, my Telegram channel is t.me/Diksha Kaushal Chemistry, Diksha Kaushal Chemistry, and on this channel you will get all my next sessions that I'm going to take on Saturday and Sunday. One will be for physical chemistry formulas, other will be for inorganic exceptions. These sessions are going to be 45 minutes each. Okay, so hardly these sessions are going to be 45 minutes to 1 hour. So you can go, on Saturday and Sunday come live in the session and watch these along with me so that we can get fully prepared for our JEE Mains attempt 2. Okay. Yes. Okay then. Bye-bye. Take care. See you all in the next class where we are going to do physical chemistry formulas. Till then, bye-bye. Take care of yourself. And I want to see your comments in the comment section. And don't forget to share this with your friends and also with your family members, with your juniors also who are right now in the maybe in the 11th class. Share this channel with your juniors as well if you think that we are providing you some quality content. Till then, bye-bye. This is Diksha Kaushal signing off. Bye-bye.